Hello everyone, it is my pleasure once again to welcome you all to MSP lecture series on transfer chemistry. This is the 49th lecture in the series. Probably I may take another 3 lectures to complete the inorganic reaction mechanisms. Then I shall move on to electronic spectroscopy and NMR spectroscopy, and then I would conclude this course, and the 60th lecture would be a concluding lecture. So, let me continue discussion on inorganic reaction mechanisms. Under that I shall focus again today on substitution reactions in octahedral complexes. And yesterday I spoke about water exchange reactions after concluding discussion on trans effect. So, let me continue from where I had stopped. You can see how the rate constant in an octahedral complex when we perform substitution reaction do not depend on atomic or ionic radii and also the charge, but of course to an extent charge can have influence, but more pronounced is crystal field effects, especially with case of transmetal complexes. When we talk about substitution reaction, we can see profound influence of crystal field effect. You can see here for 3D series the first order rate constant K for water exchange reaction vary greatly as all are high spin complexes. All are high spin complexes. Crystal field effect is also less pronounced in case of 3D. For example, if you consider chromium 2 plus and copper 2 plus, they respectively have D4 and D9 electronic configuration are very labile, and you can see the value that can tell you. And then if you consider chromium 3 plus with D3 electronic configuration, it is kinetically inert. You can see the drop in the rate. And if you consider D5 species such as Mn2 plus and iron 2 plus, and D7 species such as cobalt 2 plus and nickel 2 plus, D8 species are all kinetically labile, and of course this value itself will tell you. And when we look into vanadium 2 plus having D2 electronic configuration, this is also considerably less labile than the later M2 plus ions. So, this is some information about the influence of crystal field effect on substitution reactions in octahedral complexes. And although these trends relate to CFSE effects, charge effects are also important. I mentioned charge do have some influence. Let us look into dicationic and tricationic species. When we look into hexa aqua magnesium 2 plus, this is the value. On the other hand, when you look into hexa aqua iron 3 plus, you can see the drop, both are of high spin complexes because of the increased charge here. Increased charge makes this one less labile or little bit more stable complex. The rates of water exchange in high spin hexa aqua ions follow this trend for dicationic species. This follows this. Of course, this is very similar to increase in the atomic number. You can see more or less it follows the same pattern, except for these two. Of course, here you should recall D4 and D9 because of Jahn-Teller effect. Jahn-Teller effect is more pronounced in these two. As a result, there is some anomaly when you look into the increasing order of atomic number. It does not really follow. Of course, here also it does not follow, it is coming back. So, that means you cannot really take the atomic number, increase in atomic number or something, it goes with the electronic configuration. And when we look into trivalent species, this is the order followed by metal complexes. For a series of ions of the same charge and about the same size undergoing the same reaction by the same mechanism, collision frequencies and entropy change remain constant. The variations in rate arise from variation in delta H hash, that is enthalpy of activation. For example, what is important to remember when we perform substitution reaction is we should assume that enthalpy of activation arise from loss or gain of CFSE on going from starting complex to the transit state. So, when we go from starting compound to the transit state can have either 5 coordination or 7 coordination. So, then how this varies is what matters, the delta H hash. A loss of CFSE indicates an increase in the activation energy for the reaction and hence a decrease in its rate. The splitting of the d orbitals depends on the coordination geometry. So, we can calculate the change in CFSE on the formation of a transition state. So, now I have given some values. The calculations may make invalid assumptions because bond lengths are kept constant, and that may be unlikely. But for comparison the results make some sense. I have given the change in the CFSE on conversion of a high spin octahedral complex into a square pyramidal complex if it is following dissociative pathway, or pentagonal bipyramidal intermediate or transition state if it is following associative pathway. So, you can see here this is the CFSE difference for square pyramidal when it is going from octahedral, and similarly, and this is for dissociative pathway. And the second one, when you change the coordination number from 6 to 7 in associative pathway, assume pentagonal bipyramidal, this is the values, CFSE values for starting from D1 to D10. So, although it appears empirical, it gives some vital information. For example, Cn coordination number equals 5 is dissociative and coordination number 7 is associative, that is what I mentioned. This data show moderate agreement between the calculated order of lability and that observed ease with which one can perform substitution reaction. And of course, in case of D4 and D9, if you see the values, this is due to the net Jahn-Teller effects contribution towards the high rate you see here. So, that means crystal field splitting and the geometry ligand field has some influence on substitution reactions. So, now let us introduce another term called Eigen-Wilkins mechanism. So, what is this one? Let us try to understand. So, in a water exchange process, what would happen is an entering ligand very similar to any other ligand comes and then we get the product. So, that means we should remember that among all substitution reactions we carry out in case of octahedral complexes, water exchange process is more rapid than substitutions with any other entering ligands when we try to form a product. So, mechanism may be different, whether it can be dissociative or associative or ID or even IA, and it is not easy to distinguish between these pathways. We have 4 options to explain substitution, but it is not very easy to distinguish between these pathways. An associative pathway involves 7 coordinated intermediate or transit state. On steric ground, it is less favored than dissociative pathway, especially when we consider 3D metals. Because of smaller size, what happens, expansion of coordination number from 6 to 7 is not very easy. Of course, one can anticipate associative pathway more readily for 4D and 5D series because of the larger size, whereas in case of 3D you must have noticed less pronounced is the higher coordination number than octahedral. Even if ligands are a little bit bulky, they tend to have coordination number 4, preferring either square planar geometry or tetrahedral geometry depending upon the type of electronic configuration they have. So, a dissociative pathway looks feasible because it involves a 5 coordinate intermediate or transition state. Even on steric ground it is more favorable. That is the reason in case of 3D series, 3D metal series, if you come across the substitution reaction, we can tell with little hesitation that yes, they follow dissociative pathway. For most of the ligand substitution reactions in octahedral complexes, the experimental evidences also support the dissociative mechanism. That means for a typical substitution reaction, 2 limiting cases are observed. So, at higher concentration of Y, the rate of substitution is independent of Y, pointing to a D mechanism. So, that means the entering ligand concentration is very high, means it really do not participate in the rate determining step, that is what it means. So, that is essentially we see in case of D or dissociative mechanism, but at low concentration of Y, the rate of substitution reaction depends on both Y and the substrate molecule, that is the starting complex. So, these 2 are the limiting cases for a typical substitution reaction. So, these limiting factors are explained by Eigen-Wilkins mechanism. Now, let us look into Eigen-Wilkins mechanism in little bit more detail. Eigen-Wilkins mechanism is applicable to substitution reactions in octahedral complexes. According to this mechanism, initially a transit state complex called encounter complex, this is called encounter complex, is formed between the starting complex and the entering ligand in a pre-equilibrium step. This is very important. A pre-equilibrium step is established between the substrate molecule and entering the ligand, that is called as encounter complex. This is followed by loss of the leaving ligand in the rate determining step. Once this encounter complex is obtained, then in the slow step or rate determining step, leaving ligand departs from the metal and eventually Y secures its position in the fast step. Usually the rate of formation of this encounter complex and the back reaction to give back substrate molecule and Y are much faster than the subsequent conversion of encounter complex to the product. You should remember, this is very important. The rate of formation of encounter complex and the back reaction of encounter complex giving the substrate molecule and Y are much faster than the subsequent conversion of encounter complex into the product. Thus, the formation of encounter complex is a pre-equilibrium. So, that means these facts prove that formation of encounter complex is a pre-equilibrium state of substitution reaction. Thus, equilibrium constant Ke can rarely be determined experimentally for encounter complex, but it can be estimated using theoretical models. So, the rate determining step in the Eigen-Wilkins mechanism is given by this equation here, or this is the rate constant. So, overall rate constant or rate law can be given in this form. This is equilibrium constant into the concentration of encounter complex. Okay. So, since the concentration of encounter complex cannot be measured directly because the pre-equilibrium is a much faster one, an estimated value of K hash has to be considered, which is given by this equation here. This is the concentration of encounter complex to the concentration of substrate molecule and concentration of entering ligand Y. It is possible to measure the total concentration of ML6, that means starting complex, and that of encounter complex because it is the initial concentration of the complex. So, initial concentration whatever we have taken, so that would give you clue about the concentration of encounter complex. So, let us look into the relationship between how we can arrive at relationship between these terms. So, M total is equivalent to concentration of substrate molecule plus concentration of encounter complex. So, again here we can substitute here this one for encounter complex from this equation, and then it becomes simplifies. Now, if we take out this common, we will get this one into 1 plus equilibrium constant into concentration of Y. So, now we know the concentration of ML6, it is equal to the concentration M total, the total is nothing but these two terms over 1 plus Ke into Y. Though now we can determine the rate very readily for this reaction accounting encounter complex here. So, this is the rate equation one can think of. This is called Eigen-Wilkins mechanism. The equation looks little bit complicated, but at low concentration of Y where Ky is much less than 1, in that case the equation approximates or simplifies into this one. Since K observed can be measured experimentally and Ke can be estimated theoretically, K can be estimated from the expression K equals K observed over Ke from this equation. We can take from this equation. Okay, once you consider from this equation what would happen. So, eventually you can determine it. Now, let us look into a typical reaction of hexa aqua nickel reacting with Y to give a product. For this reaction, K values are given for various entering ligands. These are the entering ligands, various entering ligands. The K vary very little and is consistent with ID mechanism. If the pathway is associative, the rate would depend more significantly on the nature of Y. So, that means by just looking into the K values, one can get an idea about what mechanism this reaction is followed. If the pathway is associative, then we have to account for the concentration of Y as well. If it is independent of concentration of Y and with very little variation in the K values, it indicates that it is consistent with ID mechanism, or even I would say dissociative mechanism. Some values are given, you can see they are very close here. So, at higher concentration of Y, so Y is a solvent, in this case this will be much greater than 1, the rate equation approximates to this one. It will be simplified further and it would be having this value. The value of K can be measured directly as K observed equals K. So, the water exchange reaction given below, so here exemplifies a case where the entering ligand is the solvent. So, this is a very exemplified case of water exchange reaction. The experimental trends consistent with dissociative or ID mechanisms for substitution in octahedral complexes, and ID is also supported in many instances with experimental data. So, in this reaction, for this reaction, if we look into the rate of substitution increases with in the following order. So, various anions in this reaction is carried out, the order of rate follows this here. This whatever the trends I showed correlates with the mx bond strength. You should remember mx bond strength, how stable a complex depends also the what is the bond strength of that particular bond. The stronger the bond, slower the rate. If it is the leaving group, stronger the bond, slower the rate, because it takes little more time for detaching or departing the leaving group from the metal coordination sphere, and is consistent with the rate determining step involving bond breaking in a dissociative step. Of course, you should remember once again bond breaking is very important in dissociative step, whereas bond making with the entering is what matters in case of associative mechanism. So, if we plot a graph of log K, where of course you should remember K is the rate constant for forward reaction, against log K, where K is here equilibrium constant for this particular reaction with the different entering ligands. This plot is going to be linear with a gradient of 1.0. I am going to show you in the next slide. Delta G, the Gibbs energy of activation is directly proportional to minus log K, and Gibbs energy of reaction is directly proportional to log equilibrium constant. Let me show you the plot. You can see here this is linear for different entering groups here. I am referring to this group here. A plot of log K, you should remember log K, what we have taken here, this is rate constant for the forward reaction, and then what we have considered along x axis and if it is y axis. So, this is equilibrium constant for the substitution reaction is linear with gradient 1. So, thus this delta G Gibbs energy of activation and Gibbs energy of reaction have relationship in their proportional to log K and log K respectively. The linear relationship between this term and this term represents a linear relationship between delta G hash and delta G. That means Gibbs energy of activation and Gibbs energy of reaction, there is a linear relationship. So, this is called linear free energy relationship, abbreviated as LFER. So, linear free energy relationship, that means if somebody asks what is linear free energy relationship, this explanation has to be given using Eigen-Wilkinson's mechanism. The plot indicates that the transition state is closely related to this one and hence has only a weak COX interaction, and hence it is a D or ID process. This is all about Eigen-Wilkins mechanism. With this information on substitution reactions in octahedral complexes, now let us try to understand the stereochemical consequences of substitution reactions in octahedral complexes. What happens when we perform a reaction? If there is a possibility of formation of isomers, whether geometrical or optical isomers, then what kind of complexes isomers that are formed, that information is very vital. So, the reactions of geometrical and optical isomers of octahedral complexes furnish information on the stereochemical changes that accompany the replacement of one ligand by the another one. So, that means the majority of substitution reactions carried out with cobalt 3+ have provided valuable information in this regard, and some of the results go back to Werner's studies on stereochemical changes he observed while working with cobalt 3 octahedral complexes. Of course, he not only worked with cobalt 3 octahedral complexes or chromium 2 octahedral complexes, he also worked exclusively on platinum 2 complexes to understand the reaction mechanism of substitution reactions in square planar complexes. That also we saw, also we studied when I was talking about Werner's concepts, and this identification and understanding stereochemical consequences began with Werner's work and once he proposed his excellent coordination theory. So, what matters here is the specific orientation of the entering group in the second coordination sphere. That means when we are performing substitution reaction, the entering group is ready in the second coordination sphere to come to the first coordination sphere to establish a new bond where the ligand leaving group departs. The entering group may prefer to approach the metal in a position, let us take if an octahedral complex is there, the entering group may prefer to approach the metal in a position opposite to the leaving group. If it is the leaving group, it can come here, 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 here. Then this isomer, the trans isomer would yield a cis isomer, because we are talking about cis and trans with respect to this one, and if this is the leaving group and if it entering group is here in a position opposite, we get a cis isomer. Since Y is separated by 4 A groups, if you consider MA4BX or something like that, as X leaves, one of the A group moved to its position to make way for the entering ligand Y adjacent to B. So, this is how a trans isomer would give a cis isomer. On the other hand, if the entering group is Y located near the leaving group, if you assume it is a leaving group, and if the entering group also comes in its close vicinity to establish a bond, so there is no change in the structure and a trans product would result. So, similarly, a cis product is expected to yield cis if the entering group is linear, if the entering group is near the leaving group. So, however, if it is opposite to the leaving group, then a mixture of isomers is predicted. Statistically, one can say this, the ratio of cis to trans is 3:1. Okay. Let us look into some of these things in more detail with considering both dissociative as associative pathway for various complexes, even for optically active complexes in my next lecture. Until then, have an excellent time reading inorganic chemistry, and once again I thank you for your kind attention.